We're going to be looking at section 1.1 and 1.2 today, and this is going to be about transformations of parent functions. So a parent function is just the most basic function in a family. We're going to be looking at those in a minute. A transformation changes the size, shape, position, or orientation. A translation, this is only going to shift a graph horizontally or vertically, but it doesn't change the size or shape. Here are the parent functions we're going to be looking at. We have the constant function, so this would be like y equals 1 or y equals 2 or any other constant. We have a linear function. This is the most basic one, y equals x. That's just a slanted line. Absolute value function, y equals absolute value of x. This is our v shape. And the quadratic function, and this is our parabola. The domain for all of these is all real numbers. The reason we can use all real numbers is there are no restrictions on the x's that we can use. We can use absolutely anything. To write all real numbers in interval notation, we write it as negative infinity to infinity. So we're going to write these ranges. Ranges means the y values we can use. And the only y value we use here is 1. So this range would just be y equals 1. Interval notation, the only thing we can do with that is just put 1, comma 1. And this means we're starting at 1 and ending at 1. So that's how we would write that in interval notation. All real numbers, again, would be negative infinity to infinity. So this range means we're going way down here and way up here. So the range in our y values is negative infinity to infinity. For absolute value, this v shape, the lowest y value we have is 0. So as an inequality, we would say y is greater than or equal to 0. Interval notation, 0 to infinity. Quadratic, same kind of thing. The lowest y we have is 0. The highest y is infinity. Here it is in inequality form. In interval notation, it would be 0 to infinity as well. Okay, so this example says to graph f of x equals negative x squared on your graphing calculator. Write the domain and range in inequality form and in interval notation. So basic graphing on the calculator. First we want to turn it on. The on button is right there. We're going to clear everything out. Clear, clear, clear. Everything needs to be cleared out. Go to y equals. Clear anything out of here. If your stat plots happen to be on, which yours will not be on, I can just hit enter. So I want all of these to be unhighlighted. Yours probably is unhighlighted already. So now f of x just means the same thing as y. All this is saying is that we have a function and x is our variable. So I'm going to graph this. I cannot hit the subtraction key. The subtraction key cannot be used as a coefficient. I have to hit the negative key. So I'm going to have to do negative. Right here is the x button. It says x t theta n, x. And then squared is right here. So there's how I type in y equals negative x squared. Now, I could just hit graph, but that doesn't mean that we're all going to have the same screen. To make sure we all have the same screen, I'm going to hit zoom. Zoom, and I want a standard screen so that we're all the same. So zoom standard. And then now it's going to graph this for us, and that's the way it looks. So when we have this parabola graphed, first of all, we want to think, why does it look that way? Obviously, this negative in front of here took this and it flipped it upside down. And so we have this as our shape. We would write it this way. Our domain is going to be negative infinity to infinity. We can use anything on our domain. The range is going to be reading it from bottom up. So the lowest point we can have, and we can't be equal to it, so we just call it negative infinity, and this goes all the way up to 0, and we include 0. So that would be our domain and range. All right. Next thing we're going to do is we're going to identify the parent function family to which f belongs, and then we're going to describe the transformations. So this is an absolute value function. And I can see that the normal absolute value function goes like this. That's the normal one. And look at this one. Can you see how every y value has been actually multiplied by 5? So this normal y value right here is at 2, now it's at 10. So every y has been multiplied by 5. This would be called a vertical stretch by a factor of, and I'm just going to say of 5. Vertical stretch of 5. This one, the normal quadratic function is going to look like this. In this one, I can see it's been shifted over. It's actually been shifted over 1 and up 4. So this function is just going to be our quadratic, is the parent function, and it's been shifted, or you could say translated, horizontally, but I'm just going to say it went to the shift of right 1, and it went up 4. See that new vertex? Over 1, up 4. Alright, so now let's look at some other ones. It says to graph the function and its parent function, then describe the transformation. Use a graphing calculator. Alright, so we're going to graph this one. So the parent function for this is just going to be y equals x. Let's graph it. So here's going to be y equals x. I'm going to do that zoom 6. Since I've done that, I could just hit graph now, but we'll just do that. So this is just going to have a y-intercept of 1, and it's going to go up 1 over 1, or in this case up 2 over 2. So it's going to go right up through there and right down through here. Okay, so there's our parent function. Now I'm supposed to graph this, so I'm going to go back to y equals, and I'm going to go down to y sub 2, and I'm going to put this one in. 2, here's the x, minus 3. And at this point I can just start hitting graph because I've done that zoom enough. So here's my new one. Okay? So I can see now I've got this y-intercept at negative 3, and I've got this slope of 2. I can see that just from other things that I know about this. So I'm going to go up 2 over 1. Kind of hard to do on this graph, but there's 1, 2 over 1. Okay, and I'm just going to connect those dots. If you have a straight edge, you can use it. If not, no big deal. We're just trying to get the basic look of this. Okay, and so there's the new one. So what we can say then as far as this transformation went, this right here, I can think of this as two different ways actually. I can think of this as a vertical stretch of 2. We're going to just write it like that. Vertical stretch of 2. And it went, you can see, down 3. So we've done that. That's our transformation. All right, on this one, this is an absolute value function. So let's go back to y equals. Let's clear. All right, here's the clear button. Enter. Let's clear this one out. Clear, enter. I'm going to go back up to y sub 1. I'm going to put in 1 divided by 2 to get 1/2. Now, absolute value, you need to know where this is. You go to Math, you arrow over to Num, and you want ABS. That's absolute value. And I want X inside of there. This 1 is not inside of there, so I need to arrow out. So I'm going to arrow outside of there and put +1. That's this one, okay? I forgot to put in the parent function, so I'm just going to go ahead and put in the normal one. So Math, Num, absolute value of X. That's the parent function. All right, so now we're going to see what the difference is between these. So I'm going to hit Graph. So there's the new one I got. And here's the original one. All right, so the original one I'm going to do in purple. The original one is just this V shape. And actually its slope over here is just +1, up 1 over 1. Over here it has a negative slope, so it's like up 1, left 2. So there's our normal absolute value function. Here's our new one right here. So the new one, I can see it's starting here at 1. And I can also see that it's wider. Or I can also think of that as being, it's not, that blue one is actually going to be vertically shrunk as well. So it's going to 1, and then instead of having that slope of 1, it's actually going up 1 and over 2. Oops, hold on a minute. Up 1 over 2 would look like that. Up 1 over 2. All right. So this, straight edge here. It's kind of hard to do. We just want the basic idea here, though. You don't have to be exact again. So I'm just going to make it go over like that. That's fine. All right. So now we're going to describe these transformations. So to describe these transformations, I am going to have to use that terminology that we've been talking about. Well, this is going to be a couple of different things here. This is going to be a vertical shrink of 1/2, and it went up 1. Okay? Those are the things that happen. I can see that vertical shrink. It's not as steep as it used to be. It's shrunk vertically by 1/2. And this vertex used to be here at 0, and now it's up here at 1. All right, so it's just some basic terms there. Going to do a couple more just to get the hang of the graphing calculator too. So looking at this one, it says identify the function family and describe the domain and range for each of the following. Write as inequalities and interval notation. Check on the graphing calculator. So this is a parabola. So this is going to be our quadratic, is going to be the family. Okay? So I'm also going to just graph this on the graphing calculator. So I'm going to go to y equals, clear it all out, type it in, 3x squared plus 1. I can just hit graph now. I don't have to keep doing the zoom 6 because I've already done it. So here's our parabola. I can see it's been shifted up 1 unit. And I don't have to be exact here. I just want to get a kind of basic shape going. There we go. Now we're going to write the domain and range. The domain is going to be -infinity to infinity. We can use anything for x. The range is going to be the y values. The first y value we come to is 1 to infinity. That would be our domain and range there. Inequality notation, that's interval notation. As an inequality, here's how I would write it. For the domain, I would just say all real numbers. For the range, I would say y greater than or equal to 1. Okay? On the next one, I'm just going to do interval notation. Let's go here to our calculator. You should be making some kind of conclusions about what happens with these kind of graphs. We have -2. You should have some idea of what this is going to look like. We're going to go to math, num, absolute value. X minus 1 is inside that absolute value symbol, arrow out, and then +3. And graph. So it looks like this. I can see this vertex right here is going to be at 1, 3. So I'm going to go over 1 and up 3. Yeah, they make that tough on us there with these, the way the axes are. Okay, and so now I want to go down 2 and over 1. That kind of changes our slope there. And again, you don't have to be perfect. Don't waste all your time. Just want a kind of basic graph here. The domain on this, I can use anything for x, -infinity to infinity. And the range now, I'm starting way down here. We call this -infinity, and it's going up to our highest point of 3. And that would be interval notation. All right, we're just going to do a few more now, section 1.2. So now they're going to tell us what actually happens. So we have, if we have y equals f of x plus or minus h, this is going to be a horizontal translation. This is going to shift us either right or left. If we replace x with x minus h before evaluating the function, this shifts the graph right. So whenever x turns into x minus h, we go right. Replacing x with x plus h shifts the graph left. So it's kind of the opposite. X minus h takes us right, x plus h takes us left. Alright, so we're going to be looking at that here in just a minute. That's horizontal. Vertical translations. The graph of y equals f of x plus or minus k is a vertical translation of the graph of f of x, where k is greater than 0. This says adding k to the outputs shifts the graph up. Subtracting k from the outputs shifts the graph down. In this case, you're only replacing the x. In this case, you're going to add k or subtract k from the entire function. Let's look at examples. Here's the original function we're starting with. I'm going to go to y equals 2 math num absolute value x, get out of there, plus 3. That's my original function. I'll look at that. Now it says write the function g whose graph is a translation 2 units to the left of the graph of f. Here I go. Here's my original. I'm writing a new g. I have the 2. If I want to go to the left, look at the directions. I have to replace with x plus h. Our h is 2. So I'm going to have to replace with x plus 2. Oops, we have absolute value. And then plus 3. So that's what we should do in order to take this graph 2 units to the left. Let's take a look. There's my original. I'm just going to check this. You don't need to put it in, just kind of watch. X plus 2. I need to get out of there. Plus 3. And I'm going to look and see, did this shift that function 2 to the left? So let's go ahead and hit graph. Here's the original. And can you see that the new one has been shifted to the left 2 units? Original graph is in blue, new one is in red. Blue, red. Alright, let's look at the next one. Write the function g whose graph is a translation 3 units down of the graph. Let's look for down. To go down, we have to subtract k. So 3 is our k value. So I have to take my original function. There's my original, and now to take it down 3, I'm going to have to do minus 3. So my new function then is going to be 2 absolute value of x. 3 minus 3 is just 0. So here's my new function that should take it down 3. So all I have to do now is I want to keep that there because that was my original. Put in this new one, just 2 math num absolute value of x. That's my new one. I'm going to hit graph. Here's the original. Here's the new one. And can you see that that's just shifted that graph 3 units down by subtracting 3 at the end of that? All right. Moving on to reflections. If we want to reflection in the x-axis, remember this is the x-axis, this is the y. If we want to reflect over the x-axis, we have to multiply the entire function by -1. Right here, multiplying the outputs by -1 is going to change their signs. The entire function must get multiplied by -1 to have that reflection over or in, you can say either one, the x-axis. Reflections in the y-axis, that's to reflect over this. The graph of y equals f of -x is a reflection in the x-axis. Oh, that should not be there. This should go here. I just printed out wrong. So the graph of y equals f of -x is a reflection in the y-axis of the graph of y equals f of x. Alright, so now that's saying we have this, and then if we want to flip it over this line here, then to flip it, see how it's flipped? We put -x in for x. So multiplying the inputs, or the x's, by -1 changes their signs. So in this case, only the x gets replaced with negative x. Okay? All right, write a function g whose graph represents a reflection over the y-axis for f of x equals x cubed plus 5. If I want to reflect over the y-axis, x gets replaced with negative x. Here's my function. So I'm going to have to do f of negative x. So that means my x has to get replaced with negative x. And that's going to be it. That is going to be a reflection over the y-axis. Let's check it out real quick. You don't need to put it in, just watch. So my original function was x cubed plus 5. My new function is negative x cubed plus 5. All right, and so now I'm going to do my graphing. Here's the original. It's in blue. Here comes my new one. And see how that's a reflection over that y-axis. So what I did was, here's where the x is. I have to use parentheses on that. So that x was getting cubed. So I have to say my negative x is getting cubed. Yes, you could simplify that more, but we're just going to leave it as is for now. Example 2. Write a function g whose graph represents a reflection over the x-axis for f of x equals x cubed plus 5. So now we want to reflect over the x-axis. Here's the x-axis. To do that, we have to multiply the entire equation by negative 1. So here's my original, and I am going to have to multiply it by negative 1. This all has to get multiplied by negative 1, the whole thing. So my new g function is negative x cubed minus 5. That should be a reflection in the x-axis rather. So here's my original right here. My new one is negative x. You guys see how I'm getting to the caret there? That's to cube it. Cubed. Okay, once I get that, I have to arrow out of there, and I have to do minus 5. All right, let's look at it. Here's the original. We wanted a reflection over the x-axis, and look at that. See how if I folded over that x-axis, it would go right on top of one another. That's how we reflect over the x-axis. Everything has to get multiplied by a negative. Okay. Horizontal stretches and shrinks. To apply a horizontal stretch by a factor of a, replace x with 1 over ax. This will stretch all x's away from the y-axis by a factor of a. To apply a horizontal shrink by a factor of 1 over a, replace x with ax. This will shrink all x's towards the y-axis by a factor of 1 over a. Okay, little confusing, but just take it one step at a time. Here's our function. Write the function g whose graph is a horizontal stretch by a factor of 3. Horizontal stretch. Let's find it. Horizontal stretch, replace x with 1 over a. We want a horizontal stretch by a factor of 3. So I'm going to have to replace this x right here, where I have that circle. I have to replace it with a 1/3 x. And that should do a horizontal stretch by a factor of 3. It doesn't seem like it would, does it? But let's look. Math num, absolute value, x minus 2, that's our original, plus 1. Going down here, math num, absolute value, 1 divided by 3x minus 2, get out of there, plus 1. Okay, graph it. Here's the original, and here's our new one. We wanted a horizontal stretch by a factor of 3. What that does is it makes everything stretch away from that axis by a factor of 3. See how this used to be at 2? Well, now it's way over here at 6. It stretched that away. Also, see how wide this is now? Because it's stretched out further. So that is correct. Write the function g whose graph is a horizontal shrink by a factor of 1/2 of the graph of f. Well, let's look at the horizontal shrink. If we want 1 over a would be 2 in this case. So we're going to replace x with 2x. Kind of seems weird, but that's what you do. Here's our x. That x has to get replaced with 2x. And then just to prove it to you, this is the only one I need to change. And we want to see if this is going to be a horizontal shrink by a factor of 1/2. Here's our original. It should be shrunk so that it's tighter horizontally. There it is. So look, it used to be out here at 2, but now it's out here at 1 because it got shrunk closer to that axis. Plus, the whole thing got shrunk in. So that's our answer there. All right, guys. Just about finished here. Vertical stretches and shrinks. All right, so if we want to do a vertical stretch by a factor of a, we multiply the entire equation by a. This is going to stretch all the y's away from the x-axis. If we want a vertical shrink by a factor of 1 over a, multiply the entire equation by 1 over a. This will shrink all the y's towards the x-axis by a factor of 1 over a. Same equation. Write the function g whose graph is a horizontal stretch by a factor of 3 of the graph of f. All right. So I want to have a horizontal stretch. Oh, darn. This should say vertical, sorry. I'll change it so yours will say vertical. Function whose graph is a vertical stretch by a factor of 3. So if I want a vertical stretch, I want to do this. Vertical stretch by a factor of 3. Multiply everything by 3. So I'm going to have to take this function and multiply that whole thing by 3. Well, I would now just need to multiply this coefficient by 3. This is the way this would become. It would become 3 absolute value of x minus 2 plus 3. That's our answer. I don't want to multiply this by 3. It's already getting multiplied by 3. To do it twice would not work, just once. Now we want a function g whose graph is a vertical shrink by a factor of 1/2. Okay, well now I have to take this function and I have to multiply this by 1/2 and this by 1/2. So it's going to turn into this. Oops, this also. Both of those have to get multiplied by 1/2. Now let me just show you this one. 1 divided by 2, math, absolute value, x minus 2, get out of there, plus 1/2. Alright, so take a look. So here's our original function. We want it to be vertically shrunk. So look at this. See how that vertex is shrunk down? Now it's only 1/2. And look at this. It's vertically shrunk more. It's not as steep as it was. It's shrunk by a factor of 1/2. Okay, I'm just going to do a few of these just to help you out, and then you'll do some on your own. I'm going to write the answers for you, but you should pause the video after I do these 3. So, first of all, I want a translation 2 units to the left. So to do that, you can look back if you need to, but wherever I have an x, that x is going to have to get replaced with x plus 2. That would be the answer. Or you could also write this. Either one of those two would be correct. Wherever I have an x, I have to replace it with x plus 2. Taking this function right here, I want to take it 6 units down. So that means I'm going to have to take this function and I'm going to have to subtract 6. So my new function should be negative absolute value of x plus 9 minus 7. That's going to take it 6 units down. That's all I can do with that one. This one, I want to move 7 units to the right. So that means my new function, wherever I have an x, if I have a circle there, I have to use parentheses. If I want to go 7 units to the right, I have to take that x and I have to replace it with x minus 7. So my new function then for g is going to be negative 2x plus 14 plus 2, which is now going to be negative 2x plus 16. Now, that always confuses people. And here's why. I want you to look at this. Negative 2x plus 2. Here's my new one. Negative 2x plus 16. I wanted this to shift 7 units right. It doesn't seem like that's going to do that. But let's take a look. Here's my original function. I wanted it to shift 7 units right. Right now it's at 1. So my new one should be 7 units right. 1, 2, 3, 4, 5, 6, 7. Yep, that works. Even though it doesn't seem like it would, it did work. So this is my new function for g. Make sure you put g equals. On your test, you will get marked off if you don't put g equals. It's not an equation if you don't have that. All right, I'm going to do just one more with you, maybe two more with you. I'm going to do these last two, and then I'm just going to write the answers for these, and you can practice them if you want, or if you want to go on to the homework, that's fine. Number 10, consider the function f of x equals the absolute value of x. Write a function g whose graph represents a reflection in the x-axis, followed by a horizontal stretch by a factor of 3 and a translation 5 units down. This has a lot going on. My original function is this. My first step is to a reflection in the x-axis. My first step then is to put a negative out in front. I multiply the equation by negative 1 to do that. A horizontal stretch by a factor of 3. That's my second step. So my second function then, I want to replace this x that I have right here. I have to replace it with a 1/3 x. So now I've got this. That's my second step done. This is absolute value right here. My third step is I want to go 5 units down. So now I just take this function and I move it down 5. So here's my final answer. I have to put g equals. That would be it right there. Okay? Which of the transformations in 1.2 will not change the y-intercept of this? Well, let's look at this function. This would be absolute value of x, but it's been shifted up 3. It's going to look like that. So think about it. What transformation won't change this y-intercept? Well, that's going to be a reflection over the y-axis. If I reflect over that y-axis, it's going to be exactly the same thing. Okay? I'm just going to do a couple more. I'm not going to talk while I do them. I'm just going to let you can pause the video and then check later if you'd like. All right, hopefully you did well on that. That's all we've got.